We want to finish by looking at an application of sorting, solving a more difficult algorithmic problem to illustrate how sorting can play a role in so many important applications. So the idea is you've got a string. It might be a very, very long string, millions or billions of characters. And what you want to do is find the longest substring in that string that appears at least twice. It's the longest repeated substring problem. And one motivation for this is from genomics, where we have a long string taken from the ACGT alphabet. So in that case, there's a substring of length 5 that appears twice in that string, and that's the longest one. So maybe you saw that one. Here's another one. Now you can see that this can be a challenging problem even for a human to solve, and even for a computer, it's a challenge. In this case, they overlap, and maybe we want to not allow overlaps, but we'll allow it. So there's two examples of finding the longest substring that appears at least twice. Here's the first 100 digits of pi. Are there long repeats in that? In this case, not too many. Just the longest repeat in the first 100 digits of pi is just 3. So those are some examples to illustrate this problem. Here's another example. People study music to understand the repetitive structure and perhaps compare different musical compositions. So this one's, there's an arc connecting parts that repeat. This is Mary Had a Little Lamb. If you hum that to yourself, you can recognize this repetitive structure. Here's another one that's much more intricate, and maybe if you studied that for a while, it's pretty interesting the way that it builds. There's the big arc across, but the long ones in the middle are kind of build up. Quite interesting. That one's Fiorelisa. And so you can understand how this idea of things repeating is important in lots of contexts. But really, the reason that people look for repeated sequences in the real world is that it has something to do with causality. It means there's maybe something there. So, for example, is there a difference between the digits of pi and random digits? That's a kind of an interesting philosophical question. You know, we know it's not rational, it's transcendental, but is that the same as random? The answer is no, but we can't tell the difference. Any tests that people have performed on the digits of pi would pass the test of randomness. So for example, if you build a mathematical model for the length of the longest repeated subsequence, say it should be about 14 for 10 million digits, and that's what it is for pi. Cryptography. Longest repeated subsequence is important. If you have data that's supposed to be encrypted, one thing that cryptanalysts do is find the longest repeated subsequence. And why do they do that? Sometimes the people doing the encryption make a mistake and repeat certain header information. And if you read about cryptography, you can learn about famous examples of this. So you find that repeat, assuming something about the header information, that's one way in to break a code. And the other example is DNA. If you've got, in that case, if you've got a really long repeated thing, then people assume it's kind of junk, and really we want to look somewhere else for what matters. And these strings can be really long, so just one chromosome might have millions of nucleotides. So we want to be able to have an algorithm that scales for solving this problem for all three of these applications. All right, so let's take a look at it. So here's a simple warm-up called the longest common prefix problem. So we have two strings, and we want to find the longest substring that appears at the beginning of both of those strings. And we'll call that LCP. And this one's really easy. You just compare character by character until you find a thing that's not equal. Here's the code for that. Whichever is the shorter string, you use that as the termination of your for loop, and you just go through. If you find a place where a character where they're not equal the first time, that's the substring you return. And if you get through the whole thing, then you just return the smaller of the two substrings. So that's the LCP, takes two strings as argument and returns a string, which is the longest common prefix of the two strings. And we'll use that as a helper method in our solution to longest common substring. So just building on that, just our first approach to solving the longest repeated substring problem is a brute force method. And again, often we solve problems with simple methods to make sure that we understand them, and also to check on small cases our more sophisticated algorithms. Or maybe we have small cases that we need to solve in the first place. So what do we want to do to find the longest repeated subsequence? Well, we take our string that we take as input, and we're supposed to return a string, which is the longest repeated subsequence. Again, we pick off the length of the string in n. And what we're going to do is, for every position in the string, we're going to compare for every position later in the string. We're going to test whether the substring starting at I and the substring starting at j have a longer common prefix than what we've seen before. So we compute the longest common prefix of the substring from I to the end and the substring from j to the end. And so that's x, and again, that's easy to compute. And then we just check if the length of x is bigger than the length of the longest that we've seen so far. And if it is, we save x as our longest repeated subsequence. So we're trying all pairs of positions in the string to see the length of the longest common prefix starting at those positions, and those are subsequences of the real string. So a straightforward method, try all possibilities. And that certainly works for our simple example. I call it LRS brute just to distinguish it from later methods. So the analysis of this is that it's going to take about n squared over 2. It's got nested for loops for I and j. There's going to be about n squared over 2 calls on the longest common prefix method. And that method takes time proportional to the length of the prefix, so it obviously doesn't scale. So we can't consider using this method for something that's got millions of characters in it, as in the genomics application. Need a method that scales. Well, it turns out that there's a very efficient solution that was discovered decades ago that uses sorting. And here's the idea. It's called suffix sorting. So the idea is that we're going to form what's called suffix strings, which is the substring that you get by starting at each position. So position 0, that's the whole string. Position 1, it's the string that you get starting at position 1 in the original string, and so forth. So the string is of length n, there's n suffix strings. Just starting at so position 10, it's the 5 characters at the end of the string, C, A, A, G, C. So there's n of those, n suffix strings. So that's the first step in this solution. And then what we're going to do is sort them. They're just strings, so we'll go ahead and sort them. And we'll keep track of the indices that go with them, but the idea is to just sort the strings. So now we don't have to check all pairs, because the ones that have the prefixes are going to be together in the sort. So what we need to do is just look at adjacent entries. So and then find the longest common prefix among adjacent entries in the sort. If they're not together in the sort, they're not going to have as long a prefix as the ones that are together in the sort. And that's easy to see when you think about it. So in this case, it's the ones AC, AAG come together in the sort, and that's the longest one. And we can try all pairs. We're not going to see every position. We try adjacent entries, and we're not going to see a longer one than that. So that's the longest common prefix applied to the suffixes gives us a solution to the longest repeated substring problem. So let's look at the implementation in Java. So we're going to create an array of strings called suffixes. And then for every position in our string, we're going to take the substring from I to N and put that in as suffixes of I. Then use merge sort to sort it. And then same as before, except now we just look at adjacent positions. We pull out the longest common prefix, put that in string X, check if it's longer than the longest we've seen so far, and set it as before. Find the longest common prefix among adjacent entries, and that's the implementation of longest repeated subsequence. And the thing about this method is, again, works on our small case. The thing about this method is it's just got n calls on substring to set up the suffix array, and it's got n calls on longest common prefix, so at least it's got the potential to scale. And we can test that empirically. And here's the empirical analysis that we used in our course for many years, a couple of decades. So we're talking about genomics, so we'll use ACTG alphabet. And we'll take random strings. So we can use our generator. This is a generator that generates a million random string, one random string with 1 million characters in it, draw from that alphabet, which is the type of thing that the biologists need to find longest repeated subsequences. And it took just 2 seconds. And if you got something that fast, you might as well multiply by 10. So for 10 million, it'd take 20 seconds. So problem size increases by 10. The ratio of the running times is about 10. That's a method that scales. Or if you prefer, do the doubling and see that the ratio is about 2. And so that's an empirical analysis that confirms the hypothesis that the order of growth of the running time of this method is about n log n, and that time is for the sort. And you can use the highly optimized sort like the system sort if you don't want to use our merge sort. This is the way that we taught it for many years, and so, but why am I bringing that up now? That was really important discovery that you could have methods that allowed scientists to scale their study with the size of the input. In the 90s and the early 2000s, the amount of data was growing as the technology for bioinformatics was improving, and this type of algorithm definitely enabled new research and development. But a few years ago, something else happened in testing this code for this lecture. It crashed, ran out of memory. So what's going on? We had a change in the system that broke a working program, and for all we know, broke the working programs of scientists and researchers out there trying to understand more about DNA and the genetic code. What happened? Well, as it turns out, there's 2 alternatives for implementing substrings in Java. There's actually several, but I'll talk about these 2. So let's say we have this string and there's 2 substrings. So the way that it was done in Java up to 2012 was substrings were created by reference to the original string. So if genome is our original string, then it would be referenced, the actual string would be at some address X, and that memory address would be part of the data associated with genome along with the length. And then the substrings could just be different addresses within that original string. So there's no need when you take a substring to copy any characters. It's just a matter of saving away those indices which can be computed in constant time and also take constant space, just a pointer and a length. That's the way that Java strings were designed for the first couple of decades. But since 2012, they decided to change the representation to one where when you take a substring, it would copy the characters to make a new string. Now, the reason they did this is people would have huge strings like the contents of a web page, and they would take only a small substring out of that huge string and hold on to it. Even though they only needed a small number of characters, Java couldn't reclaim the memory for the original huge string because of this organization. So it allowed the potential to free up a lot of memory when the original string is no longer needed. But unfortunately, what we saw is that this requires linear time and space to implement substring. And that's why our programs broke. So this is not too hard to fix. What you can do is implement our own constant time operation, which imitates the old implementation. We have to implement a compare to method to enable the sort, but that's not too big a deal. And the details of this are covered in our algorithms course. So Alice, for example, is in good shape. And if we do that, then even today we can find longest repeated substrings in huge strings in a very small amount of time. So lesson is trust the algorithm. This algorithm was around before Java. It'll be around after Java. You want to trust the algorithm, not the system. And people are continuing research and development in these kinds of areas. Just one final note. We're running this longest common prefix. It turns out that the running time is going to be quadratic in the length of that longest repeat. And in our model, we don't have any long repeats, but real data actually has long repeats. So people have developed more sophisticated algorithms than this one that are guaranteed to run in linear time, even faster than sorting. Just to indicate the care people are taking and the importance of scientifically analyzing performance of algorithms in the way that we're doing it. So the summary is that we have an efficient algorithm to search and sort an array, we have an efficient algorithm to sort an array, and we have many, many things that are enabled by fast sort and search. The important idea is the scientific approach to understand the performance of our algorithms by building a mathematical model and validating it with empirical tests. Very natural in all kinds of areas of science, and it's particularly important in computer science. We're not just hacking to get a problem solved. We're understanding performance, and performance matters. So Alice has got her IPO going, and Bob is rethinking the idea of a hackathon. Maybe he'll take a few CS courses. So that's our introduction to the second part of our course.